So there are control instructions. I think it's not shared. So there are some logic instructions, CMP, RM, that is comparing the contents of the accumulator and the register contents. That is, A is less than the register contents. A is equal to the register contents. A is greater than the register coordinates. Then the carry flag is set in case A's contents are both are same. Then zero flag is set. Then A contents and the contents is greater than the register contents, then the carry and zero flag will be set. Then CPI, that is the 8-bit data. The 8-bit data and the accumulator contents both will be compared. So accumulator contents is less than the data, so that the carry flag is set. Then accumulator content, the data is both are same. Then the zero flag is set. If K is the contents of A is greater than the data sent, then carry and zero flags both will be reset. So this is what the comparison instructions. Then logically and the contents of the accumulator and the contents of any register or memory, both will be ANDed. So the result will be kept in the accumulator itself. And this instruction is ANI 8-bit data. Any 8-bit data and the accumulator content both will be ANDed, and the content will be stored in the accumulator. And this is XRA, the exclusive OR operation between the any register content or memory and the accumulator contents. Both will be ORed, and then the result will be stored in the accumulator. Then again in the XRA 8-bit data, any 8-bit data and the contents of the accumulator both will be compare exclusive OR, and the data will be result will be stored in the accumulator. Then the OR operation, any register content and the contents of the accumulator are ORed, and result will be placed in the OR accumulator only. Then ORI 8-bit data, that is 8-bit data and the 8-bit data along with the contents of the accumulator both will be put it in the accumulator only, 8-bit data, and be odd, then result will be stored in the accumulator. Then rotate left accumulator. So one bit will be moved to left. This is a 8-bit data will be moved. One bit will be left to this. Each bit of the accumulator is placed rotated left by one position. Then bit D7 is placed in the position of the D0 as well as in the carry flag. So carry flag is modified according to the bit D7. So S and P, AC are not affected. Then the rotate accumulator right. So one position will be moved to the right side by one position. Bit D7 is placed in the position of D7 as well as the carry flag. The carry flag is modified according to the bit D0. Then rotate accumulator left through carry. So the contents of the carry and accumulator contents one bit will be moved. So each bit of the accumulator is rotated left by one position through the carry flag. Bit D7 is placed in the carry flag, and the carry flag is placed in the least significant position D0. So CY is modified according to the bit D7. So then it is similar to the left RAR. Rotate accumulator right through carry. Each bit, binary bit of the accumulator is placed rotated right by one position through the carry flag. So bit D0 is placed in the carry flag, and the carry flag is placed in the most significant position D7. So carry CY is modified according to the bit D0. Then they complement the accumulator, the content, whatever the complement, ones will become 0 and zeros will become 1 in the accumulator contents. Then complement the carry flag we can make it a zero. Zero will become 1 and 1 becomes 0. Then we can set the carry by STC instruction. Then the branch instructions, there are two types of branch instructions, conditional and unconditional instructions. The JC, JNC, JP, JM, JZ, JNZ, JP, JP0 are the condition instructions. The conditions on carry, condition on no carry, jump on positive, jump on minus, jump on 0, jump on no 0, jump on parity odd. So these are the carry flag positions as basing on the position whether the carry flag is set or reset, and it will be jump accordingly. So similarly, all other flag contents will be checked and it jump according to the instruction. Then there is a unconditional instruction. This will be used in the subroutine. So call with followed by address, then it jumps to that particular location. This is possible. This is used in the case of subroutines. And there's another conditional also will be there. This will be call instruction on carry, no carry, positive, minus, 0, 0, parity, even parity, and odd parity. So on these conditions also it will jump. Then this as the call instruction jumps to that, then at the end of the program we write the return instruction, that is RET. So automatically it goes back to the main program. So this is also again jumps back, return back on some conditions like carry set, carry no carry will be reset, positive number if it is a negative number, or zero flag is set, zero flag is reset, or parity is even, or parity odd. These are the conditional return instructions. Then the contents of the program counter are copied with the HL content, so that the program starts with the address of the HL contents, HL pair contents, so that jumps to that particular position. This is the restart 0 to 7 positions. So RST0 to RST7, there are 8 positions are there. Similarly, there are 4 interrupts that can be written, trap, and RST 5.5, RST 6.5, RST 1.5. These are the instructions. Then coming to the control instructions, no operation, halt, disable interrupt, enable interrupt, rim, sim. So here, this in no operation, there won't be any activity. So it will just jump to that particular, it leaves that and then it jumps. So this will be useful when you want to modify the main program instead of changing the addresses of that, we can use this NOP so that there won't be any change in the program. So then halt and enter halt wait state. So this is the end of the program, we write HLT. Then interrupts using this, the interrupts of the trap are disabled. So we can, using disable interrupt and enable interrupts, we can program it. Then sim and rim instructions both are useful for interrupts and also the SID and SOD pins of 8085. That is serial input data and serial output data is possible with these two instructions. So this is all about the instruction set of 8085. So let us try switch over to some of the instructions, programs. So let us start with the simple addition program. Addition of two 8-bit numbers. This is the simple program. So here, let us discuss this type of program. This is LXH, that is the memory initialization as C050, and during this uh, program, this M is defined as the contents of C050. Then the contents of M will be placed in the accumulator. Then incrementing the H, that means C050 will become C051, that is the next address location. Then the contents of this C051 and the accumulator will be added, these two numbers. Then the position, the STA will be stored, that is storing the contents of the accumulator into the location C052, and the program will be halted. So to execute this before, then we have to write two numbers in this particular address location. 50 is placed in this, and 05, 02, let us say. So this is stored in this location, and executing, assembling, and step by step we'll write the program. Now the contents are to be going to load into the accumulator. F50 is loaded into this accumulator. Then the incrementing the HL pair as C051. Then addition of memory contents of C02 is 02, which you added to this. So 0 by 2 will become 52. Then this 52 will be stored in the address location C052. So this program is altered. So this is the end of the program. This is one simple program. Next is decimal addition assembler. So decimal addition program, here also you need to store decimal addition of the 8-bit numbers, sum of 16 bits, then manual store first number in the memory location C051, manual store second number in the C051 location, and result will be stored in C050, 52 and 53. So let us store some data in the location as C, which is 45. Then in the address location 5 to 5 AL put. So this is the data that is stored, and let us execute the program. Then now this memory is initialized, and the counter is C00, moving the memory contents to the accumulator. The increment the contents of the memory, that is C051. Then addition takes place. 45 is added to this, so 9F is the result. And DA is the decimal adjust accumulator. The contents of that will become 05. Jump to the address location, incrementing this and storing this into the address C to A, and storing the contents of the accumulator, and halt the program. So this is the end of the program. So 0150. So result is 0150, which is equal to the numbers that we stored for 4, 5, and 5A. This number equal to 0105, that is 105. So actual number is 45 plus 4, 5A is equivalent for 80 plus 90. So 90 plus 135 is the number. So 105. So 105 is the decimal equivalent number. This is the jump instruction with jump on carries is took place, and some of the instructions. So this comes under one of the loop instructions, and this is an instruction. The Fabness serial number to run the program. Simply load the memory location C051 with 01, C051 with is 01, and then start. So let us store 01 in 01, and this is also with 01. Then run this. With the loop instructions. So it is storing the numbers. To the loop. So this is the final result of this program. So this is how the program, the loop program takes place. That's all about the programming part. Then we'll switch over to the next part, which is interfacing of before that yeah, this talks about the addressing modes. Yeah, this is the all about the data transfer, input and output organization, When information received from an external device is usually stored in the memory for later processing. Information transferring from central computer into the external device organizes the memory unit. The CPU merely executes the I/O instructions and may accept the data temporarily, but the ultimate source or destination is the memory unit. The transfer between the central computer and the I/O device may be handled in a variety of modes. Some modes are use the CPU as the intermediate path. Other transfer data directly to the memory unit. So data transfer to and from peripherals may be handled in one of the three possible modes. That is programmed I/O, interrupt initiated I/O, and direct memory access. So programmed I/O, in this, it is due to the result of the I/O instructions that are written in the computer program. Each data item transfer is initiated by an instruction in the program. Usually the transfer is from a CPU register and a memory. In this case, it requires constant monitoring by the CPU of the peripheral devices. The transfer of the data requires three instructions: read the status of the register, check the status of the flag bit, and branch to step 1 if not set, or key step 3 if set, read the data register. So here this is one simple diagram that we can see. This is the CPU, this is the interfacing between the IO device and the CPU. So the address will be sent to the IO device, and data bus is also connected to this, and IO read and IO write. So based on the necessity, so the data will be accepted by the IO device, and data will be sent to the this particular interfacing register IC, and then data will be received by the processor. Now in this three processes, programmed IO, the drawback is, the main drawback the program initiated was that the CPU has to monitor the units all the times when the program is executing. Thus, CPU stay in the program loop until the IO unit indicates that it is ready for data transfer. This is the time consuming process, and the CPU time is wasted a lot in keeping the eye to the execution of the program. To remove this problem, an interrupt facility and special commands are used, which is called as the interrupt initiated IO. So in this method, the interrupt command is used to inform the device about the start and end of the program. So whenever the data is ready, it will be received one interrupt signal so that the processor time will not be wasted, so that again it will be sent a interrupt acknowledge, and it will be ready to receive or send data. In the meantime, the CPU executes other program. When the interface determines that the device is ready for data transfer, it generates an interrupt request and sends it to the computer. So when the CPU receives such a signal, it temporarily stops the execution of the program and branches to a server program. And the interface determines that the device is ready for data transfer, generates an interrupt request and sends it to the computer. When the computer CPU receives such a signal, it temporarily stops the execution of the program branches to the service program to process the IO transfer, and after completing it, returns back to the task what it was originally performing. The CPU responds to the interrupt signal by storing the return address from the program counter into the memory stack, and then control branches to a service routine that processes the required IO transfer. The way that the processor chooses the branch address of the service routine uh, varies from one unit to another. In principle, there are two methods for accomplishing this. Vectored interrupts. In a vectored interrupt, the source that interrupt supplies the branch information to the computer. Then non-vectored interrupt. In a non-vectored interrupt, the branch address is assigned to a fixed location in the memory. So these are the two vectored and non-vectored interrupts is possible for interrupt initiated IO. Then the third one is the direct memory access that are transferred between the fast storage media such as magnetic disk and the memory unit is limited by the speed of the CPU. So thus we can allow the peripherals directly communicate with each other using the memory buses, removing the intervention of the CPU, the type of data transfer, a unique technique is known as DMA, direct memory access to memory. The CPU is idle and it has no control over the memory buses. The DMA control takes over the buses to manage the transfer data between IO devices and the memory unit. So data transfer will be taken care by this particular device. Then next part we want to discuss is yeah, this is the next part is the uh, interfacing part. The interfacing of 8083 and 8255 both will be discussed briefly. So the program 80 not is it is 808253 is a timer. This is again manufactured by the yeah. So the 8253 is a IC timer IC. Then it is manufactured by Intel, and this particular 808253, the IC pinout diagram, uh, the block diagram, which consists of uh, three counters: counter 0, counter 1, counter 2. So this will generate various outputs, and it has data bus buffer and read-write control and control word register. This is available with this. The interprogram interval timer designed for the microprocessor top upper from timings and counting functions using 316-bit registers. Each counter has two input pins, clock and amplifier and gate, and one pin for output. So to operate the count, a 6-bit count is loaded its register. On command, it begins to decrement the count until it reaches 0. Then it generates a pulse that can be used to interrupt the CPU. So what are the features of 8255? If you look at, it has 3 independent 16-bit down counters. It can handle inputs from DC to 10 MHz. These 3 counters can be programmed for either binary or BCD count. It is compatible with almost all microprocessors. 8254 has a powerful command called read black command, which allows user to check values. So these are the data connected from the 8085, and these are the output signals. Basing on the programming, we can get the outputs. Now let us see how to interface 8253 timer chip with the Intel 805 microprocessor from the following picture. We can see that the data bus D7 to D0 of 805 is connected to the data pins of D7 to of 82553. So the higher order address bus is used as a decoder input to select the chip, and the A8 and A9 825 are connected to the pin number A1 and A0 respectively to the counter. So these are the A8 and is connected, and these are the decoder connected to the chip select signal. So this data bus is also connected to this input. Then is D0. So the higher order address bus is used as decoder input to select the chip, and the A8 and A9 of 805 are connected to the pin A1 and A0 respectively to select the counter. In the next diagram, we can get the chip. This is what it is. IO by IO read and IO write. So A1, A2 are the cell, and these are the chip select signals. So this is also selected to so that A4. Then only the chip select pin 825 will be enabled. So this is showing the counter is being selected by using the A1 and A0 pins. This is A0 and A1, 0, 0, 0, 1, 1, 0, 1, 1. So this is in total 10, 11, 12, and 13. These are the for counter 0, the command code is 10. To select counter 1, it will be 11, and counter 2, it is 12H. For control word register is 13. So this will be used in programming. By using this in and out instructions, the counter selection and control word register setup can be done. If the accumulator is holding content to load CWR control word register, then by using out on 13, the CWR will be set. Similarly, by using in instruction, we can get the value of the counter value, like 1N, 11H will be get the value from counter 1 and so on. So the following 4 steps are needed for counter operations. Initializing the 8253 chip, then load control word register with control word value, load lower order count value, load higher order count value. So let us see a program to load two counter 2 in a mode 1 with a count value of 500 in mode 1. So count 0 is 10110010. But count to 1000, and these are the don't condition, clear condition 00. So this is simple program. Move B2 to A, load B to H. So A is initializing by the counter out 13, right? This is to control word, and this is 88. Load ls byte of count value, then send counter to output is on 12, then 13, and out on 12, then move D comma 00, clear the register contents. Then A will be stored with 80, again 12, and A to B, and send 12, or the contents, then all the program. So we can, by selecting the chip select, we can select this chip, and by sending the control signals, read bar, and A1, A0, and then by sending the data, we can, whatever the signal that we want, we can generate from this. Then coming to 855, this is a program with peripheral interfacing IC, which is also called PPI. It is an IC used to simplify the interfacing of microprocessor and microcontrollers with I/O devices and increase the number of I/O devices that can be interfaced. The best part is that it is programmable, which means that we do not have to change circuit connections and wiring in order to switch between the different ports and modes of operation. Make sure you'll understand working of 8255 before we begin this. So you can have a look and how it works in different operation modes. In this, we can cover the interfacing of 8255 with 8085 microprocessor. We will take up this example and we'll do it. So there are the component required 085, IC74, LS373, one NAND gate, one NOT gate. This is all about the 8085 microprocessor, and this is 8255 PPI, peripheral interfacing IC. Reset out is connected, read bar signal, write bar signal, I bar by M bar signal is also connected to this. I bar by M bar is connected to the NAND gate. 1, 2, 3, 4, 5. And then one buffer, address buffer, which is also connected to this ALE. So ALE is connected. ALE is used to address latch enable signal to demultiplex the higher lower address and data bus. Then data bus is directly connected to this, and address bus, some of the address lines are connected to the NAND gate here, and then it will be connected to pin number 20C chip select signal is connected to chip select signal. Then VCC ground as usual, it will be connected to that. We can understand the connections of the following step. We need supply VCC and ground, reset out, read bar, write bar, and the air is all discussed. So there is one output demultiplexer, so that we can be this can separate the address and data bus. Then the last part of making connections is chip select signal. Chip select signal is for port A, it will be 20, for port B 21, port C is for 22, control port is for 23. The last two bits, A0, A1, the rest of the 6 bits are used to generate chip select signal. So we are taking the only lower right bits of the address into the consideration, because here we define the ports A, B, and C, IO mapped IO and not memory mapped IO. So IO mapped IO has 8-bit address, memory mapped IO has a 6-bit address. So this is the control word, how it will be required, port C, and so port C is selected, so D0 will be for output and input, these will be written here, and for port B given, and for D2 is for port B, and port C, port A. What mode? Mode 0, mode 1, mode 2, and BSR mode and IO. So these are the different modes. Ports will be working IO mode and not in BSR mode. D7, this is simple IO operation. So we need all 3 ports A, B, and C is output mode. Therefore, D4 is equal to D1 is equal to 1. D3 is equal to D4. The control word would be 1001 and 0010 in a binary, 92H in hexadecimal. Now we write this data to control word to set the port into the desired modes. So this completes this step 1. Step 2, this is the control word. Then step 2, read from the port A. Input will be stored in the accumulator, but we need to read another input from port B, and hence we move this data to register C. So read input from port B. Then now we have to have the 2 numbers to be added in the accumulator and register C. So we add both of them and output the value to port C. So assembly language program for 8255. So this is the program, moving mediator A, 92H, and load the control word into the accumulator. Then write the control word, the control port 8085, read the input from port A, then the contents, whatever is stored in accumulator, move to C, then take again another data from the another port, then these contents and added C content both will be added, then output port result with the addition of port C, etc. So these are the various instructions, the programming, simple program to interface 8255 and 8253 IC timer, and also IO peripheral program peripheral interfacing IC. So this is all for this today. So this is the end of the program.